warm welcome again, and welcome back to ATAL Faculty Development Program on the electric vehicles. Today is the third day, and today we have with us Professor Praveen Kumar from IIT Guwahati to enlighten us on the electric vehicle charging infrastructure and integration of electric vehicles to grid. Uh, Sir is currently serving as professor at IIT Guwahati in the Department of Electrical and Electronics Engineering. He did his BTech at NIT Hamirpur in 1988, MTech at IIT Delhi in 2000, and PhD at Delft University of Technology in the Netherlands in 2008. He has guided 10 doctoral theses and is a senior member of IEEE since 2016. He has one patent in his credit. Sir has more than 100 research articles published in reputed SEI journals, transactions like IEEE, ITA, etc. He remained as research assistant in the Department of Electrical Engineering at University of Stuttgart, Germany. He served as electrical engineer in AVL Trimerics GmbH, Der System, Elmocat Engineering GmbH, Germany, and as manager in Drivetrain Innovation VV. With vast industrial experience, he joined IIT Guwahati in 2009. His areas of expertise includes design of high power and torque density motors for electric vehicle applications, advanced induction motor design and prototyping, vector control of motors for EV drivetrain, and smart charger including wireless power transfer. Sir is presently looking after e-mobility laboratory and executed various collaborative projects related to EV. Sir, excuse me if I have missed out any significant contribution from you. Thank you, sir. Thank you, sir, for being with us. We are privileged to have you with us. And now, sir, I would like to request you to kindly take over the session, sir.
Thank you. Thank you very much, Dr. Singh, and good morning to all the participants. So, I'll just be sharing my screen, and please do let me know if you can see it.
Yes, sir.
So I have, okay, I don't have the sharing right. So can you please make me the presenter, Dr. Singh?
I think, sir, you can present.
It shows me I don't have the privilege to share the screen. Now I think yes.
Yeah,
Are you able to see my screen, all of you?
yeah, it is coming, sir. It is coming.
And the PPT is visible?
Yes, very much, sir.
Okay.
Mm.
So yeah, we will be talking about chargers, and eventually we will be looking at the integration of EVs to the grid. So all that has to be done via a very robust charging infrastructure. Now, to understand all that, I think the first point to start with is the basics of the charger, because then we will start to understand the complexity that once we start to do any kind of a large scale grid integration or large scale of charging infrastructure rollout, then what are the exact problems that we face and why it is not a trivial problem to address. So there are many research papers, many books written about grid integration, but once we start to look into the technology in detail, then we start to realize that yes, there are many finer points and nuances that we have to pay attention to before any kind of a smooth integration to the grid can happen, smooth integration of the EVs. Okay, and the interface that we have between the grid and the EV are the chargers. So let's first have a look at them. Here on the screen there are two broad categories of chargers. So one is the AC charger, the first one that we have here. So these are the AC chargers, and sometimes they are also known as level 1 and level 2 chargers. And next, what we have on the screen here are the DC chargers, and they are also known as level 3 chargers. So now if we see the difference between the level 1, 2 and 3 chargers in terms of voltage, the power, and also the approximate time to charge the battery, then this is the comparison that we have here. So level 1 chargers are mostly used or predominantly used for residential applications, and one can operate them at 120 or 230 volt AC depending on what kind of a grid supply we have, and the maximum current can go up to 16 amperes. So usually 12 to 16 amperes is the current range on which these chargers work, and they are all work on single phase power supply. And the power that can be drawn depending on the voltage and the current rating is around 1.4 to 2 kilowatt. So that's the maximum power that can be drawn from this charger and injected into the battery. And so, for example, if we have an EV, a normal car, electric car, so that would have a battery of roughly 24 kilowatt hours. So that's becoming more or less a standard. So to charge the entire battery pack of that car, we would need around 17 hours. So the philosophy is that you come home in the evening or late afternoon at around 6 p.m., and then you plug it to the charger, and by morning 6 or 7 the battery is completely full. So that's the idea of this kind of a charger. So it's really a very slow charging. Then we have something which is known as the level 2 charger. So level 2 charger still belongs to AC charger. Okay. So in level 2 chargers are mostly used in commercial applications. So commercial applications, like you go to your office and then you park your vehicle, so there would be some chargers at the parking place, so that's a commercial establishment. Or you go for some shopping to some mall or somewhere, and then if you park your car and plug it to a charger, then that's a commercial charger. Or any other such establishments. Okay, so these are the level 2 chargers, and they again have a voltage range of 200 to 240 volt AC, and the maximum current can go up to 80 amperes. And that's again on single phase or split phase. Okay, and the power that can be extracted, the maximum power that we can get out of the battery is 19 kilowatt, and the minimum power that these chargers have is around 3 kilowatt. And on an average, you would be able to charge your 24 kilowatt hour battery in 8 hours. Okay, so that means if you extract 3 kilowatt hour power, then in 8 hours the battery would be charged. So here the philosophy is that you come to the office and you can plug in your vehicle to the charger, and the vehicle would be in the parking lot for 8 to 9 hours, depending on the office hours, and in that duration, it would be topped up. Then we come to the next category, which is the level 3, also known as DC chargers. Okay, so in DC chargers, we can go from 300 volt to 600 volt DC, and these are all polyphase systems. So we have a three-phase power supply, for example, we convert that into DC, and then it is connected to the vehicle. So the output of the charger is a DC, and here we can go up to 240 kilowatts maximum power currently with level 3 chargers, and they can charge a 24 kilowatt hour battery on an average in around 30 minutes. It can be even faster. Okay, now these kind of chargers are suitable for installations on highways. For example, if you want to take up a long journey, so definitely you can't afford to wait for 7 hours nor 17 hours, nor can you afford to wait for 8 hours. So one has to charge the battery in a very short duration of time, so they have to be then DC chargers. But here again, we have to think that there are certain challenges that one has to overcome. The first thing is that how fast a battery can be charged depends on the charger, of course, but it also depends on the battery chemistry. So is the battery chemistry suitable for very fast charging? If not, then even if we have a fast charger, the battery won't accept the energy at a very fast rate. So we cannot really use a fast charger on a battery which cannot accept energy at a very fast rate and expect that in 15, 20 minutes or in half an hour I will have a full battery. So we should have a compatible battery as well. So that's point number one. Point number two is that a vehicle can have an AC charger, or it can have a DC charger, either of the two. Okay. So now if you have an AC charger on your vehicle and you come to a charging station which is a DC charger, then that is not compatible. So we have a compatibility issue. So the best scenario would be that a vehicle has both AC and a DC charger. Now that of course is going to add to the cost of the vehicle and also will result in some increase in the weight. So if you see here from the figure, it's very clear the philosophy of AC and the DC chargers are quite distinct. So we have the grid and then we have EVSE. So it is electric vehicle service equipment, which is the general name for the charger. Okay, so the output of the charger is AC and it goes into the socket of the vehicle. Clear? And the vehicle accepts AC, converts that into DC, the required DC level, which the battery would need, and with the help of the BMS, the battery pack gets charged. In case of a DC charger, the output of the charger is DC. Okay, and that goes into the DC-DC converter of the vehicle, and there that DC-DC converter charges the battery pack. So you see here, in case of an AC charger, we would need a rectifier inside the vehicle, whereas in case of a DC charger we don't need a rectifier. But if we have a vehicle which can be used with an AC charger or and DC charger both, then we need a rectifier as well as DC-DC converter, and we need to have a bypass mechanism. So the BMS has to identify whether the socket that is connected is an AC charger socket or a DC charger socket. If it's a DC charger socket, then it has to bypass the rectifier and activate the DC-DC converter. So all that algorithm has to be built. It should have at least two sockets, one socket to accept AC charger, the other socket to accept DC charger, and it should also have an additional rectifier, so that if you use an AC charger, still the battery pack can be charged. Plus it should have a bypass mechanism, so if you connect the DC charger to the vehicle, then the rectifier has to be bypassed. So these are all kinds of complexities that would be associated if you want to have a vehicle which can be charged with a DC charger as well. So this is from the charger topology point of view inside the vehicle, and also we have to ensure that the battery pack that the vehicle has is capable to accept energy at a very fast rate. Okay, so these are the two issues that one has to look into before deciding to what kind of a charger should the battery be connected to. So one thing is very clear, which is a common issue many EV users face, is that they have a battery pack which is not suitable for fast charging. They connect it to a DC charger and the battery does not get charged in 15 minutes or half an hour. It still takes 7 8 hours. The reason is that the battery was not suitable for rapid charging, and that leads to frustration. Okay, and the other point which we have to also keep in mind is that the lithium ion battery chemistries which can accept very fast charge are pretty expensive. So if we are going to be very cost sensitive and we expect that the EV has to cost quite low, okay, then we won't be getting those advanced battery chemistries inside the vehicle. And if we don't have the advanced battery chemistries inside the vehicle, then we won't be able to do any kind of a rapid charging. Now, having said that, there are two main categories of classification of the charger. So one that we saw here is level 1, 2, and 3. The other category of charging, which we have another standard, which is given by IEC, is mode 1, 2, 3, and 4 charging. Okay, so mode 1 charging is slow charging from a regular electric socket. It can be single phase or three phase. Okay, then mode 2 charging is where we have a charging from, it's a slow charging from a regular socket, but there are some EV specific protection arrangements in the charging infrastructure. Like it would have dedicated isolators and circuit breakers for the charger. It would have temperature sensor to see whether there are any hotspots inside the charger or not. Okay, so it will have all those kinds of additional protection system. So mode 1 with additional protection system becomes a mode 2 charger. Then we have mode 3 charger. So in case of mode 3 charger, uh, it can go up to fast charging. Okay, and it has a multi-pin socket. So mode 1 and mode 2 do not have a multi-pin socket, they have a normal socket to charge the vehicle. But mode 3 has a special socket, where because we need to communicate with the BMS. So mode 3 chargers would be able to communicate with BMS, and that communication with BMS is very, very important if we want to go for fast charging. If we restrict ourselves to slow charging, then communication with BMS is not necessary. Even if we do not have a BMS in the battery pack, it still is okay. But as soon as we go into any kind of a fast charging, then the battery pack must have a BMS, and the BMS must communicate with the charger. Okay, so for that we have special sockets. Okay, either we use SAEJ1772 or IEC62196. These are the two very common sockets which are used for mode 3. And then we have mode 4 charging, which is known as fast charging or ultra fast charging. And one of the examples of that is char demo. Okay, so char demo is one which allows us to do very rapid DC charging. And besides classifying them into the various modes, okay, so the if you see, the various modes can also be mapped into the levels. So level 1 and 2, okay, levels 1 and 2 would actually be mode 1, 2 and 3. So mode 1, 2 and 3 fall, or are similar to level 1 and 2 given here. And level 3 is same or similar to mode 4. So now those levels 1, 2 and 3, they are mostly used in North America, and these modes 1, 2, 3 and 4 are mostly used in Europe or the European Union. Clear? So these are two different standards, one for North America, one for Europe. So far they are not compatible. Okay, so there are discussions and talks on compatibility of these two big standards which we have worldwide. Clear? Now, which one India would adopt finally is still an ongoing debate. Should we go for our own kind of a classification of charging, or should we adapt any one of the two? So far, the picture is not very, very clear. But maybe in coming time, we would have a clearer picture of what exact charging standard we are going to use for our country. Then there are cases. Okay, so cases of connections associated with the modes. So we have case A. So case A is any charger connected to the mains and is usually associated with modes 1 or 2. So if you are operating in mode 1 and 2, then you have a case A connection or case A category of connection. Then case B is onboard vehicle charger. Okay, and that is associated with usually mode 3. The onboard charger is same as AC charger. So when we say onboard, so the rectifier and the DC-DC converter are both placed inside the vehicle. The output of the charger is plain simple AC. So AC charger or onboard charger, they mean one and the same thing. So we should not get confused that what is an onboard charger and what is an AC charger. So onboard charger and AC charger are one and the same thing. It means essentially that the output of the charger is AC, and on the vehicle we have a rectifier as well as a DC-DC converter. Okay, now, if we go for case C type of a connection, so that corresponds to mode 4. Okay, and in this case, we have the output of the charger, which is DC. Okay, so that means the rectification and everything is done by the charger, and the output is DC, and that goes into the battery or into the vehicle. Clear? And once we have that kind of a connection, that is a case C type of a connection, and it is usually associated with mode 4. So you can see now gradually the level of confusion increases. We have level 1, 2, 3 type of chargers. Then we have mode 1, 2, 3, 4 for chargers. Then we have case ABC for chargers. But if you do one to one mapping, then you would see that there are similarities. Okay, there are similarities between all these three. It's just that different countries and different geographic locations are adapting different kinds of standards. So here we can see a clear difference between the conventional internal combustion engine vehicles and EVs. So if you have an ICE vehicle or an internal combustion engine vehicle manufactured anywhere in the world, and if you directly import it to India, you can run it because the petrol or the diesel standards throughout the world are same. Okay, a petrol the ICE engine made in Europe or made in North America or made in Japan can be used with the petrol or the diesel that is available in India without any problem. But in case of EVs, we have all these kind of complications. Okay, and all these kinds of complications, what we have seen so far, results in different kinds of connectors, different kinds of voltage levels, different current levels, and hence the compatibility becomes a big issue. Okay, to unify the charging code, the best work is done by European Union. So to start with, every country in European Union had its own charging code. Okay, but then there was a problem. Since European Union is a borderless community, people can travel from one country to the other without any problem. So if you have an EV in Germany and you drive it and you go to France, for example, and then you find that in France they have a complete different standard for charger, you are unable to charge your vehicle, you are stuck there. You can't move a kilometer if your battery runs out of charge. Okay, so recognizing that problem, they started to unify the code in the European Union. But still, there is a lot to be done to unify the code and to come to a universal charging standard for all the countries. Okay, that is going to take time, but that is a need. And also, it's not such a non-trivial problem, because the thing is that the grade of different geographic locations or different countries are different. In some countries we have 60 hertz power supply, in some countries we have 50 hertz power supply, in some countries we have 120 volts at the domestic output, in some countries we have 220 or 240 volts. Okay, so there are differences within the grid itself, but it's not a problem which cannot be solved. To a large extent, that problem has been solved by electronics industry. For example, if you have your mobile phone, okay, if you buy it in India, you can take that mobile phone to any country in the world and you can charge it from the socket. You have adapters, okay, socket adapters. You can buy them and you can use that adapter for any kind of a socket anywhere in the world, and it is you don't need to worry about the voltage and the frequency levels, because the electronic inside the mobile phone takes care of different voltage levels and different frequencies. Okay, so the problem has been solved, of course, for low power application, because mobile phones don't consume that much of power when they are charged, but the problem is still the same and there has been a solution. So similarly, for EVs we will have to find a solution so that the interface of the EV with the charger in any geographic location can be a seamless one. Okay, the only difference here is that, or the challenge that we have to face is, the power levels are higher. Okay, so power levels are higher, that should not be a very serious concern, but the major concern would come in how do we design the plug points so that they can or how do we design the adapters so that it can be plugged into any kind of a socket anywhere in the world. Okay, so those are the work that we will still have to do to make sure that the EVs become universally accepted and it becomes easy to drive an EV and go from one geographic location to the other geographic location. And here are some of the examples of different kinds of connectors which further add to the confusion. Okay, so if you see here, for type there's a type 1 connector which is SAEJ1772. It is used for level 1 and level 2 charging in North America, and here is the Psi connector. Okay, it is also used for mode 1, 2, and even for mode 3 in the European Union. Okay, a very famous connector which you must have seen in many of the literature. Then there is another European connector, which is VDEARE 262322 connector, which is which can be used for level 1 and level 2, and can also be used for mode 1, mode 2, and mode 3. Okay, so if you look at these two, they both can handle same levels of power, but you can see the way the connectors look are very, very different. So if you have a vehicle with a VDE connector and you go to a charger which can accept only SAE connector, then the vehicle is not compatible with your charger. Okay, so for same voltage levels, for same power levels, we have two very different connectors and both are popular. Then we have a combined charging system, which is known as CCS, a very popular one, which is good for level 3, and this is the connector for level 3 charger. Then we have char demo, which is also compatible with level 3 or level or mode 4 in case of EU standard, and the connector looks like this. So both the CCS and char demo, they can handle the same amount of power, they can handle the same voltage level, they can handle the same current level. Okay, but look how different the connectors are. So if you have a vehicle with a CCS connector and you go to a charging station which is a char demo charger, then again your vehicle is not compatible. Okay, so it's not only the levels of voltages, levels of current, different charging standards which are a problematic area, but the connectors are also a problem area. So a lot of standardization has to be done. A lot of compatibility issues still exists. So until and unless these are clearly addressed to, we cannot have a very large scale development of charging infrastructure. And if we do not have a very large scale charging infrastructure, then we cannot expect to have large scale penetration of EVs on road. Okay, so there are many, many issues and they are all interconnected. So the point is that until and unless we really address this basic level of issues, then expecting to have vehicle to grid and so on is a far-fetched dream. We do some research on V2G and how vehicles can be connected to the grid and so on, but those are all theoretical studies. There are practical problems at the ground which have to be addressed first, and only then we will be able to do any kind of a serious grid to vehicle integration. Now, having done that, let's see the difference between the public chargers and the residential chargers, because that's again a very critical point once we will look into the integration of EVs into the grid. So, public chargers, for example, they are a part of the of a network. So, when I say network, it means it's a part of the grid itself. Okay, because public chargers would have a very high utilization rate. Or most of the time some vehicle will be connected to the charging point, they would be continuously delivering power to the grid and power to the vehicle and extracting power from the grid. Okay, so they have to be a part of the entire grid network. So grid has, for example, if you see the distribution network, it has protection system, it has transformers, it has grid monitoring systems and so on, and eventually it would have chargers. So chargers cannot be considered as a separate entity, but it has to be included as an entity into the grid. Okay, it should be a subset of the grid itself. Okay, then the other thing is that it requires local user authentication. Today what happens is that if you have a public charger, okay, you need to get permissions from the grid operator to establish a public charger. It's not that you can just buy the charging equipment, and then put up a charger anywhere you want to. You need to have proper permission from the distribution company of the area. The reason is that the EVs are kind of an unpredictable load on the grid. All other loads that we have on the grid are more or less predictive, and we have a fair idea of how the power demand on the grid would vary in a 24-hour cycle, and that is all based on the historical data. Now, today, since we don't have much of an EV, and as the penetration of EVs would increase, for some initial years, we will have no idea to predict what would be the low power requirement from EVs at different hours of the day. Maybe after 15, 20 years of extensive use of EVs, we will have a lot of historical data, and from that historical data we will start to gain insight that when would the peak charging hours for the EVs would happen. Okay, but till then it would be an unpredicted load. So we need, there are a lot of regulatory frameworks for setting up the charger. Moreover, the public chargers have a back channel communication. Okay, so it has a communication to communicate with the grid and also with the BMS, because public chargers can support fast charging. So if a charger supports fast charging, then it must communicate with the BMS, and also it should communicate with the grid to know the status of the grid. Okay, if the grid is already under stress, then the charger should not allow too many vehicles to have rapid charging. It should restrict it. Otherwise, it would not be healthy for the grid. Okay, so it should have a lot of communication infrastructure associated with it. Also, the public chargers usually will be at level 2 or level 3 from the North American standard, or they would be at level 3, mode 3 and mode 4 from the European point of view. Okay, because no one is going to connect their vehicle to a public charger for 17 hours. Okay, at a public charger, the maximum duration, by public charger I mean the dedicated charger, the maximum duration that the vehicle would be connected would be around 1 hour or 1.5 hours, not beyond that. Okay, we can't really expect that a person would come and plug the vehicle and wait for 17 hours at a public charger. That's not going to happen. So that's why they would be level 2 or level 3. Okay, level 3 deployment today worldwide is not on a large extent because of the extreme cost associated with it. So level 3, if you see, it goes to higher power levels. It can go up to 200, 300 kilowatt power. Okay, so if a charger, that means a single plug point can deliver 300 kilowatt of power, then you can imagine that how expensive the entire system is going to become, because then you need a lot of protection to interface the charger to the grid itself, and you need a lot of protection to interface the charger to the vehicle. So you need a lot of protection at the grid end and also at the vehicle end to interface them, and that adds to the cost. Okay, now if we see the residential chargers, then they would usually be at level 1. That means it will take 16, 17 hours for the battery to charge. Okay, because we, of course, from a normal plug point at home, we cannot get more than 2.5 kilowatt of power. There can be some people, okay, who might take a three-phase power supply for their home. That flexibility would come. Okay, so maybe if you are a regular user of EV, then level 1 charger would not be suitable. Okay, so if it's not suitable and you want to have frequent use of EV, then you would like to install level 2 charger at home. So if you would install level 2 charger at home, then single phase is not the best choice. You will have to go for split phase or multi phase. Okay, so you will have to take a dedicated connection. And that would be the reality which would happen if we have large scale EV deployment. Okay, if you want to put in a level 2 charger at home, then you would have to have a dedicated AC line, which I told you, because a normal domestic line won't support level 2 charger because they will draw higher power. Okay, and if you recall, the power drawn by level 2 would be around from 3 kilowatt to 19 or 20 kilowatt. Okay, so 20 kilowatt of power coming out of a socket is not a regular thing that we have in domestic situations today. Okay, but that will become a reality in near future. Also, if you will go for level 2, then you would also need to have communication network installed in the charger, because once you start to extract 20 kilowatt power and put that into the battery, then you need to communicate with the BMS, and you also would need to communicate with the grid. Okay, because if the grid is already stressed, let's say we are talking about 7 p.m. in Indian scenario. So between 5 p.m. and 10 p.m., the load on the grid in most of the Indian cities is the maximum. Okay. So now in that duration, if you want to charge your EV and you want to extract 20 kilowatt of power, okay, then it's going to create a problem for the grid. And if many people want to do that in a locality, many people want to charge their vehicles at 20 kilowatt power each, then it's going to create an havoc for the grid. Okay, so the charger need to have a good communication with the grid, should sense that what is the status of the grid, and based on that, the charger should advise the user, the EV owner, that do not go for 20 kilowatt charging right now. Okay, or there can be a dynamic pricing. So the charger would say that if you go for 20 kilowatt of power right now, then it's going to be extremely expensive. So it would defer the charging to some later duration of the night. Okay, so to do all that, it needs communication network, it needs to communicate with the grid to estimate what is the status of the grid. It needs to communicate with the BMS, because for any power levels more than 3 kilowatt, a robust communication with the BMS is necessary to know what is the state of health of the battery while it is being charged. And it also needs to communicate with the user. Okay, it's not necessary that the user will be next to the charger all the time. The user would be somewhere at home or at some other location, so it needs to communicate the user via the mobile phone or any other device or the computer or so on. Okay, so it needs to do communication with multiple entities, so it should be enabled with communication technology, wireless communication as well as wired. The communication between the BMS and the charger would be a wired communication. The communication between the charger and the grid would be a wireless communication, and the communication between the charger and the user would again be a wireless communication. So you see, a charger will not just be a power electronic system, but it would involve a lot of communication backbone as well. Otherwise, we won't have so-called seamless integration of the chargers with the grid. Now, if we look at the layout, okay, so the layout of the level 1 and level 2 charger, okay, would be something like this. So here you have the plug point, and if you see the plug point, there are 5 pins here. Okay, so the charger has 5 pins. So the first pin, or pin number 1, would be for line 1. Pin number 2 would be again the AC line 2. So at home, like we have a live, a neutral, and an earth. So you have a line, a neutral, and an earth. So these are the 3 pins that would be used. So pin number 1, pin number 2, and pin number 3. So like we have in our domestic sockets. Then we have 2 more pins, pin 4 and pin 5. So pin 4 is the control pin, okay, or the control pilot. So the job of the control pilot is to communicate with the BMS. So any communication between the charger and the BMS will be done via pin 5. Okay, pin 4, sorry. And pin 5 would be the proximity detection. So proximity detection means it will check whether the plug point is properly connected to the socket of the vehicle or not. Is the connection secured or not? So all that will be determined by pin number 5. So this would be the pin diagram for level 1 and level 2, and for domestic applications we would be using this. Now, will the plug point look square, or will it look round, or will it look like rectangular, or will it be oval in shape, and so on? That is yet to be decided. But one thing is for sure, once we go for large scale rollout of EVs and also the EV chargers, then the plug points will have at least these 5 points. Okay, otherwise we won't have a secured EV charger. So now let's look at the internal layout. Okay, so this is the cable point here. The example which I have taken is actually J1772. That is the Society of Automotive Engineers, or SAE connector. So this is the SAE connector, and which goes into the vehicle. And apart from that, you would have all this electronics. Okay, all this electronics to ensure communication with the BMS, to ensure that all the protection systems work properly. Okay, there would be relays for protection. To operate the relays, there would be transducers, so you would need to measure the voltages and the currents to determine whether they are in the safe range or not, and depending on that, it would be decided whether to operate the relays or not. Okay, so all that security system would be managed by the electronic hardware which would be present inside the charger. So apart from just this connector, there would be all this associated electronics in the charger to ensure the safe integration of the vehicle to the charger and charger to the grid. Without this, okay, it would not be a safe charger. Safety is a critical point. Okay, and to ensure the safety, we would have to go for this. So it would have the measurement subsystem, it would have the communication system, and the communication system can be based on Zigbee, Wi-Fi, cellular network, or the mobile network. Okay, so it can be any one of these communication systems, or maybe more than one of them. So it can be a combination of Zigbee, Wi-Fi, and cellular. Okay, or it can have any other new protocols of communication as and when the technology improves. It would have a wired communication. Wired communication is a must to communicate between the BMS and the charger, because that communication will happen through pin number 4. So that is a wired communication. So that is what it would have. Then it would have a processing subsystem. So the charger continuously measures the voltages and the current from the grid. Okay, and it gets the information from the BMS via the wired communication. So based on the measurement done at the grid side and the measurement done, or the information coming from the BMS, it will take certain decision. The decisions would be that, should we go for fast charging right now? Should I allow 20 kilowatt of power to flow into the battery? What would be the proper the current and the voltage level for the battery? When should I stop charging? Is the battery getting overheated? So all that information would come to the processing subsystem, and based on all this input, it will start to make decisions. Okay, and the decisions would be that, how much current should flow into the battery? Is the battery full or not? Should I pause the charging right now? Should I continue the charging right now? So on and so forth. Okay, so all that decision would be done by the host processing unit. So this is a layout of a kind of an intelligent charger which is compatible with level 1 and level 2 charging. And if we see, zoom in further, then what do we need? We need some isolated AC to DC power supply. So these are the rectifiers. We would need some isolated DC to DC converters. So these are all low voltage. low power ones, because they have to power the communication system, they have to power the measurement system, and they have to power the host processing subsystem, which is a microprocessor. So all these need power, and that power will come from the grid supply by using this power supply unit. Okay, so this power supply unit will be converting the grid supply to 12 volt or 16 volt, depending on uh, what voltage levels different subsystems of the charger need. Okay, and apart from that, we would also have a media rich user interface. Okay, so that the user can also see on the display of the charger itself that what's exactly happening, what's happening to my battery, what's happening on the grid, and so on. Okay, so that would also need the power. So this is all about the low voltage power supply. And the high voltage power, which is actually taken up by the grid, by the battery, would be given by the output of the cable here, which are the pin numbers 1, 2, and 3, would be used for actual injection of the current into the battery. And all this is for monitoring, communication, decision making, and display of information to the user. So this is how the typical layout of the charger would look like. And we do have some chargers now today available in the market which have all of these features included. And these features increase the cost of the charger. So if we don't have them, then the cost of the charger is pretty low. But without them, we don't have a secure interface between the grid and the vehicle. So we need to understand that the charger is actually an interface a an EV and the high voltage grid. Okay, and that interface has to be a robust, secured, and an intelligent one. And all this that we see in green color actually adds to the intelligence of the and the security of the charger that we have. Now, to see how the charger works, okay, so I'll just try to show you how the internal circuitry of the connector actually looks like. Clear? So here we have the controller for the charger. Okay, and here is the actual connector. So if you see here, there are 5 pins: 1, 2, 3, 4, and 5. These are the 5 pins at the charger end, and these are the 5 pins at the vehicle end. Okay, so you have the male and the female part of the charger. So this is the connector of the charger, and this is the vehicle inlet. And if you see here, the pin numbers 1, 2, and 3 would be involved in transfer of power between the charger and the vehicle, whereas pin 4 would be used for communication between the charger and the BMS, and pin 5 would be used to see whether, or used to determine whether the connection is done properly or not. Okay, and all this is based on very very simple register networks. Okay, so you have some registers on the charger side and some registers on the grid side, and using the value of the resistances, all kinds of communication can be done. Okay, for example, if this switch S3 is pressed, that means this is connected. So the resistance R7 would be short circuited. If it's not connected, then resistance R7 is not short circuited. So the current would flow from pin number 5 via R6 into R7. Okay, if it is connected, if S3 is closed, then the current would flow from R6 via S3 and go to the ground. So the resistance R7 would be bypassed. Okay, so simple resistive network which will ensure the communication with the grid, and will also see whether the proximity detection is done or not. And so far, the values of the resistances that are given here are again a standard. So this has been standardized already. Okay, so if you have the charger side, then you will use two resistors which are marked R6 and R6 here, and their values will be 150 ohms and 330 ohms. It cannot be any other value. It's a standard now. And on the vehicle side, you would have R2, R3, 4, and 5, and the corresponding values of the resistances are given here. So it is 1.3 kilo ohms, 2.74 kilo ohms, 330 ohms, and 2.7 kilo ohms. Okay, so these are all standardized. And now, if we see how this is going to work, so first of all, we will see the communication. Okay, the communication which will be done by the pin number 4. So what happens is that the charger will initially generate a high frequency pulse width modulated signal. Okay, and the frequency of the pulse width modulated signal can be 1 kilohertz or 2 kilohertz. Okay, so that's again getting standardized, and the voltage level of the pulses would be between 12 volts and minus 12 volts. So that's again getting standardized. So between plus 12 volt and minus 12 volt, the pulses would be generated. So you see here, initially the charger would produce a pulse of a 12 volt value. It will be fluctuating between minus 12 volt and plus 12 volt. So as soon as the charger is connected, the proximity is detected. So via the pin number 4, a pulse of this type would go into the vehicle. The BMS will detect this pulse. Okay, so once the BMS detects this pulse, then what would happen is the magnitude of the pulse will fall from 12 volt to 9 volt. So the BMS will reduce the magnitude of the pulse from 12 volt to 9 volt. So as soon as the pulse, the voltage of the pulse falls from 12 volt to 9 volt, then the charger knows that the BMS has detected the charger. Then what the charger would do is it will send a 9 volt pulse at a duty ratio, let's say, of 50%. Okay, so 50% duty ratio means, let's take an example, that the charger is capable of delivering 60 amperes of current. Okay, the charger still does not know how much current can the battery accept. So what the charger will do is that it will now send a pulse with a duty ratio of 50% at 9 volts level. So 50% duty ratio would mean that the charger is ready to deliver 30 amperes of current. Okay, now the BMS knows that the charger wants to deliver 30 amperes of current because it's a 60 ampere charger. The duty ratio that the charger is sending is 50%, or the pulses at which the charger is sending, the duty ratio at which the charger is sending the pulses is 50%. So that means the charger is willing to give me 30 amperes of current. If the BMS thinks that this is a good enough current for my battery, then what the BMS will do is that it will reduce the magnitude of the voltage from 9 volt to 6 volts. Then the charger will sense that, oh, my voltage level has fallen from 9 volt to 6 volts. That means the BMS has accepted. And it will start to inject 30 ampere of current into the battery. For example, the BMS started to send a pulse of with a duty ratio of 50%. BMS does not react. Okay, BMS does not react for 3 cycles. Then the charger knows that the BMS cannot accept 30 amperes. So what it would do is that it will reduce the duty ratio. So if it reduces the duty ratio to, let's say, 25%, again 9 volt pulse at a duty ratio of 25%, then the BMS will know that the charger wants to give a current which is 1/4 of its rating. Its rating is 60 amperes. but now it's sending a pulse of 9-volt magnitude, but at a duty ratio of 25%. Okay, so 1/4 of 60 amperes means 15 amperes. So the BMS will get a sense that, okay, the charger wants to send me 15 amperes. Okay, on the other hand, the charger will wait for 3 pulses. So if within this 3 pulse duration, the BMS reduces the magnitude of the pulse from 9 volt to 6 volt, then the charger knows that, okay, the BMS is ready to accept 15 amperes. If not, then it will change its duty ratio. So this communication will keep on happening until the BMS and the charger, they come to an agreement that how much is the exact voltage current level that the battery is going to accept. Okay, and as soon as the agreement is reached, the BMS will reduce the magnitude of the pulse from 9 volt to 6 volt, and then then the charger knows that the BMS is ready to accept the desired current, and the charging will happen. So this is the kind of a communication that will happen between, or happens, it has become almost a standard now, that happens between the BMS and the charger. So whenever you are trying or thinking about developing a charger for level 1 and level 2 application, then this is the standard communication protocol that you will have to implement. Okay, and today you don't need to worry anymore about how it can be implemented. There are ready-made chips available, so you can put those ICs on the charger side as well as on the BMS side, and they will take care of this communication. Okay, you don't need to program anything. So since they have become a standard, so we have dedicated ICs that can do this communication. But this is the philosophy behind the communication that happens between the BMS and also the charger. This is just about the charging. Okay, it starts to get very complex. So BMS senses the, for example, the BMS senses the internal temperature of the battery. So based on that temperature, the BMS would convey the message to the charger that reduce the current level. The battery is getting overheated. Okay, so all that complexity can be built up. But again, all the communication will happen on this kind of a philosophy, simple exchange of data, and that exchange of data depends on two parameters: the frequency of the pulses, which is governed by the duty ratio, and the magnitude of the pulses. So you can have three voltage levels right now: 12 volt, 9 volt, and 6 volts. Okay, you can have more voltage levels, maybe if the BMS reduces the voltage level to 3 volts, it means the battery is getting overheated. So the charger would sense that the battery is getting overheated, so I need to reduce the current, and so on. So you can have multiple voltage levels. Okay, they need not be in steps of 3 volts. You can also have between steps of 1 volt or 2 volts or 1.5 volts or whatever it might be. Okay, but the communication between the BMS and the charger will happen in this fashion. Okay, so this has become more or less a standard now worldwide. Now if we see about the proximity sensor case. Okay, so this is how the proximity would happen. So once we plug the charger into the vehicle, then this switch S3 would close. Okay, so when this switch S3 closes, you can find out the equivalent resistance of the entire circuit, and from there we can detect what are the voltage level at this pin. Okay, so there are again three standard voltage levels. You can have 4.5 volts. So if the voltage level at pin number 5 is 4.5 volts, it means the socket is not connected to the vehicle. If you have 3 volts, okay, it means that some human being has lifted the socket in its hand. Okay, so if you take the socket in your hand, there is a button which by default you will press with your fingers. So that means the socket has been lifted up by an operator or the EV owner. So that means you have pressed a button, and as soon as you press the button, the voltage level at pin number 5 will fall down to 3 volts. And then once you insert the socket securely into the vehicle, okay, then the voltage level at pin number 5 will fall to 1.5 volts. Okay, now depending on which voltage level you have at the pin, the charger would sense whether the socket is connected, whether the socket is lifted, and whether the socket is inside the vehicle securely. And all that would be done by these resistances or the values of the resistances. So here the connection between pin number 5 at the charger end and pin number 5 at the vehicle end. So we will now see, just I'll give you an overview, I'll give you the PPTs. So in the PPTs you can see the detailed mathematical calculation of how the voltage levels will happen. So you see, initially the pin number 5 is powered by 5 volts, 5 volt voltage source. Okay, so if you see the output voltage, here you have 5 volt, 5 volt connected to resistance R4, which has a value of 330 ohms. Okay, so what is the voltage that you will get at pin number 5? It would be 4.5 volt. And how would you get that? You see here you have 330 ohms here and 2.7 kilo ohms here. So it's a voltage divider rule, and the output voltage at pin number 5 is 4.5 volts. As soon as you connect the socket, okay, you have just connected it, you have not released the lock, the lock is not yet released, just the connection is done. So you have these two resistances at the vehicle end and additional two resistances from the charger end gets connected, but you have not released the lock. Okay, so your output voltage at pin number 5, if you do again the voltage divider rule, here the equivalent circuit is given. So if you do the voltage divider rule, then the output voltage at V out would be 3 volts. Okay, so that means the socket is connected but not yet secured. So once we release the pin and it is secured, then this resistance at the charger end will be short circuited. The equivalent resistance looks here, and again using the voltage divider rule, you will see that the voltage at pin number 5 will drop to 1.5 volts. So then the BMS and the charger know that the secured connection is done, because the voltage at pin number 5 is now 1.5 volt. Once the charger and the BMS both detect 1.5 volt, then the charger will send those pulses which we have seen earlier via pin number 4, and the communication between the BMS and the charger would happen. Okay, so all this goes behind in this simple act of connecting the plug point to the charger. So this is the first level of communication that happens between the charger and the battery. Okay, so that's why we don't have just pins on the charger, but we have 5 pins. So one for communication and one for sensing whether a secure connection is done or not. Okay, and this forms the basis of a secured EV charger. Now, this was the first point which I wanted to discuss with you, so that you get an idea or a sense of the complexity that is involved in the charger. Okay, because if I just talk about smart charger, charging infrastructure, grid integration, then we don't get a sense of what exactly happens at the hardware level. Okay, this is not the complete story, it's a part of the story to show you that at the ground level, at the hardware level, all this happens by the simple act of connecting a charger to the vehicle, or the plug of a charger to the vehicle. So this is the first part of the talk. Now I open the floor for discussion. Let's have a short Q&A session, and then we go into the other details. So anybody from the audience, if you have questions, then uh, we can start discussing them now. You will have these slides. You can see these derivations. So it's nothing very complicated. It's basic circuit which is used. So anybody with any questions? And first of all, please do let me know, were these things already discussed? I hope it was not a repetition.
No,
In
no, sir. It is not a repetition.
Yeah.
Any questions from the audience?
Hello, sir.
Yes.
Sir, actually, whenever we are running that line for signal transmission closer
Hmm.
to the high voltage transmission line, by that time signal is severely interrupted for communication.
Hmm.
So how that is tackled actually? Because high voltage transmission line is very much closer to the actual signal line. So how to
Oh,
tackle this
oh,
problem?
these are wired communication. So in wired communication, at that frequency level, the interferences are very low, because you see the communication between the charger and the BMS will happen at a higher frequency. So at higher frequencies, the interruption from the power line is very low. That is not a problem at all. And it's a wired
Okay.
communication. So wired communication always has less interference. It's always the when you go for wireless communication, you will have more interference.
Thank you, sir.
Yeah. So
Hello.
yes, yes, please.
Sir, good morning, sir. I am Dr. Saran from Chennai.
Yeah.
Is there any possibility of varying the resistance due to the temperature? Because based on the resistance value, you are selecting what is the voltage, everything, current,
Yeah, yeah,
everything.
yeah. So that is taken care. So when I say the voltage will be exactly 5 volts, there would be tolerances involved. And those tolerances would be taking into account the variation of the resistances with temperature. And moreover, we have to understand that the current involved in that circuit is extremely low. So the risk of having high temperature because of current is not there. The currents would be in milliampere range.
Oh. No, no, not because of current, sir.
Yeah,
Because of based on the region where we are using, if the
yeah. So
temperature rises,
so ambient temperature. How much can the ambient temperature go? Really, tell me.
maybe in some region it is 40 plus
Yeah. So
Celsius.
does that really impact the resistances, the ceramic resistances that we would be using? How much would the resistance change? Let's say from 2.7 kilo ohm, how much would it change?
I don't know exactly the value, but
Not much.
if
Not, it would be less than 0.1%.
oh,
So that's no serious change at all.
okay, sir. Thank you.
Yeah. Okay. So there is a question on the chat box. In G2V mode, what is the impact of grid fault on the battery? Well, we haven't come to G2V, but the impact on the battery is nothing, because there are I showed you there are isolators. Okay, so they would immediately open and the charging process will immediately stop, and there would not be any impact on the battery because of any fault on the grid. So there are two levels of protection. One is between the grid and the charger, and the other one is between the charger and the battery, or charger and the vehicle. Okay, so no impact of grid fault on the battery, because the charger will isolate itself from the grid as soon as a fault is detected, and the vehicle will isolate itself from the charger. The charging would stop. Yeah. Any other question?
Yeah, any other questions from the audience? Okay, I think, sir,
Yeah,
there's
then
no question. Yeah.
so
So,
we
sir,
will continue. Yeah,
sir,
please.
just one question from the slide, sir. sir, can you can share the slide again?
Just a second. Yeah, I'll just be sharing now. Mm, yeah, can you see the slides?
Yes, sir.
Yeah.
Sir, please go back, sir.
Yes.
Previous. Where you were showing some voltage, sir. 12 volt, 9 volt, like that. Yeah, this one, sir.
Okay. Yeah.
Regarding the duty cycle, sir, actually I find it little difficult to understand this like change in the voltage and just can you just repeat for 2 minutes or 3 minutes like that? I'll get the point.
Yeah. So first of all, the charger will send a pulse of 12 volts.
Yes, sir.
If the BMS detects that pulse,
Yes, sir.
then it will reduce the magnitude of that pulse. So how can the magnitude of a voltage pulse be reduced? What is the common way?
Magnitude of the voltage pulse, sir.
Yeah. How do we reduce the magnitude of the voltage?
Uh, uh, Not the current, sir.
Hmm?
Voltage.
Yeah, voltage. So how can you reduce the magnitude of the voltage?
Okay, sir. We can use maybe some voltage controller.
And other simple things,
We can have some devices which can control the voltage, sir.
such
Maybe
as
switching devices.
no, this pulse is coming from the
Uh,
charger
yes,
and you are receiving it.
yes, sir.
Then you retransmit at a lower voltage level. Is that possible or not?
Yeah, it is possible, sir.
Yes. And how is it possible? You will
Uh,
use your own PWM generator.
yes, sir.
So that's how the 12 volt received by the BMS. If
Mhm,
BMS receives, then its PWM generator gets activated and
mhm,
it produces a pulse of 9 volt.
mhm.
And the charger sees 9 volt.
Okay,
Okay.
yes, sir.
Yeah. So 9 volt, if it falls from 12 volt to 9 volt, that means the
Mhm.
BMS and the charger have established a communication.
Okay, sir.
It means the plug point is securely connected to the vehicle.
All
So
right.
after that is done, then the next question comes is that how much current should the charger transfer to the battery?
Okay.
So for that, the charger, let's say if it's a 60 ampere capacity charger,
Mhm,
and it sends a pulse with a duty ratio of 50%, a 1 kilohertz pulse with a duty ratio of 50%.
mhm.
That means the battery's BMS gets the message that the charger wants to give 30 ampere current.
Okay, half.
Okay.
Mhm,
If the BMS, then BMS will wait for 3 cycles.
mhm,
If it does not get a response back from the sorry, the charger will wait for 3 cycles. If it does not get the response back from the BMS, that means 30 amperes is what the BMS does not want. So it will maybe try 70% duty ratio. It will wait for 3 cycles. If no,
sir,
then it
that is,
means
sir, one
yeah,
second. I want to interrupt. So that is the point I just did not understand. Sir,
yeah.
wait means wait for the what, sir? Because it has already got the signal that it has to reduce to 50%.
No. The BMS and the the battery, sorry, the
Yeah.
charger does not know how much current the
Mm-hmm.
the battery needs.
Okay.
So
Okay.
you'll start with an initial value.
Okay. Okay. Yeah. It's
So
kind
you
of
start with
iterative. Yeah.
50%.
Mm-hmm.
Okay. Then the BMS will wait for 3 cycles. It will send 3 pulses.
Okay. Okay.
If no response
Okay.
happens, that means 50% is not the desired value.
Sir, response means like this is okay or not okay kind of thing.
Yeah.
Okay. Okay. Fine.
If it is okay, 50%, then what the BMS will do is it will
Mm.
send a pulse
Mhm.
at 6 volts.
Okay.
That means BMS has agreed.
Hmm.
So if the charger does not receive a pulse of 6 volts, that means BMS has not agreed.
Okay.
Then it will keep on changing the duty ratio
Mhm.
until the charger receives a pulse of 6 volt from the BMS.
Mhm.
As soon as it gets a pulse of 6 volts from the BMS, then the charger knows that yes, that duty ratio is acceptable to the battery.
Okay, sir. Now clear, sir. The point
Okay.
is clear. Okay. Thank you so much, sir.
So it's a simple communication that will happen between the
Yeah.
two.
Good. Good.
Okay.
Thank you, sir.
Yeah. So any other question from the audience?
I can see, sir, another question.
Sir,
Yeah, please.
Yeah.
sir, in this case, actually, at first charger is sending some signal, PWM signal to the BMS.
Yes.
So, and it is trying several times whether this particular strategy is okay or not, the signal is okay or not.
Not
And the
signal.
BMS is
Is the required current or the current level is
right,
okay
right,
or not? Yeah.
right. So, in that case, yeah, the charger is trying several times actually, either increasing or decreasing that particular this thing, changing the PWM signal.
Hmm.
So in this case, instead of doing that things, actually the BMS will directly give the signal what is its requirement to the charger itself by using some code.
For level 1 and level 2, we don't have that technology yet.
Okay,
And we also have to imagine that these two are electronic devices.
yes, sir.
They are not human beings talking to each other. That
Yeah,
I
yeah.
need 15 amperes. The charger says, yes, I can give you 15 amperes. So that kind of a communication which two human beings have is not possible. All the communication between two electronic devices has to be based on an algorithm.
This is simplex mode of type of transmission.
Excuse me?
This is simplex type of mode, actually simplex or duplex mode transmission. This one for communication.
That I won't be able to answer right now, but what do you exactly mean by simplex and duplex mode?
Only this will be initiated from the charger side itself.
The
Charger
first
to the
communication is initiated by the charger, and then the BMS has to respond.
sir.
Actually,
Yeah.
sir, shall I?
Yes. Yes. Yes.
Actually, it has only two lines for communication, so it is
Yeah.
duplex mode of communication, sir.
Yeah. 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 Duplex.
And then,
Bidirectional, I would say.
yeah. So, and then, is there any research possibilities in BMS, sir? It's
In
not in research possibilities in BMS.
Oh, a lot. BMS are very unreliable today. Very, very unreliable.
Oh,
We don't even know how to find out the state of the health of the battery accurately. It's all a rough guess, a rough estimation. That's what the BMS are able to do today. BMS is a big, big challenge. So
need to
first
say
thing,
that algorithm for working of BMS not
yeah,
yet properly proved, is it so?
yeah, the BMS is unable to estimate what is happening inside individual cells accurately. It can just make a rough estimate, a rough guess of what's happening in individual cells. But it does not, today, it does not have the ability to find out the proper status of every cell. So that is why the state of charge measurement, the state of health measurement, and so on are just an estimate.
In that case, why can't we go for a single cell instead of going multiple cells and combining these together to make a particular
So
voltage and current? Is it?
it's not possible from the chemistry point of view. You can't have an electrode for a 24 kilowatt hour battery. I mean, that would be a huge electrode. We can't even manufacture that.
Oh,
So that's the chemistry. You see, you can imagine these are all made from prismatic cells or pouch cells, and each cell is 2.2 volts or 3 volts, or depending on what kind of a chemistry we have. And many such cells are combined together to form a pack. Now, if we are talking about just one cell of that capacity, then the electrodes would be huge. and maintaining the same chemical consistency over a large surface area and a large volume is practically impossible.
Oh, it is in the chemistry way.
Yes.
Okay,
Yeah.
okay,
Yeah.
okay. Thank you, sir.
Yeah. So, yeah. Any other point?
Sir, I think
Yeah.
we have last question in the chat box. I think what are the main parameters which effects on the comparability between the EV charger and CS?
What is CS charging station?
Yeah, Devanand Jiblekar. Sir, can you please speak up so that you can clarify your question?
Okay, CS means the charging station. Well, charger
Mm,
and charging station, I would consider them to be same entity. So the parameters that affect the compatibility is the type of connector. That's point number one. Point number two is what is the battery chemistry that the vehicle has. So these are the only two parameters. So if you have a battery chemistry which does not allow fast charging and you bring it to a DC charger, then it's no point. Fast charging will not happen. Second is if your vehicle has a SI connector and you bring it to a charger that accepts VDE connector, then again we will have a problem. So these are the two major factors. Beyond that, nothing.
okay, sir. Thank you, sir.
Yeah,
Sir, I feel that I think
we can
you wanted
continue.
to yeah, sir, regarding sir that difference in the socket, sir,
Yes.
the difference in the number of pins and all, sir,
Yeah.
what exact parameters are actually making these differences?
You
Uh,
see, for example, like in a DC charger, we
yes,
will have 4 pins.
correct,
We won't have 5 pins.
correct, sir. But
And
again,
then
among the AC chargers, there
among
are
AC
also
charger, the differences are that
yes,
in case of SI connectors, pin number 1, 2, and 3 are involved in power transfer. Pin number 4 is for communication. Pin number 5 is for
yes.
proximity sensing.
It was clearly
If
mentioned.
you take the VDE connector, then pin number 1, 2, and 3 are for power transfer, but 4 and 5 are interchanged.
Okay, okay,
Okay, and moreover the layout of the pins. So in case of psi connectors, the pins are laid along the periphery of a circle. In case of a VD connector, they are on the periphery of an oval. So these are the differences.
correct, sir. I
so
think
so
Devan, yeah, Devan, and I think this answers your question. I think. Okay.
yeah.
Uh, Yeah, I think, sir, that was the last question.
Okay.
Sir, it depends on you now, sir. If you wish to take a rest for a few minutes, it's fine. And
Okay, so
otherwise,
it's 12:22. Then
yes,
let's start at 11:22. Let's start at 11:30 in another 10 minutes.
sure, sure. No issue, sir.
Okay. Okay. Yeah.
So, dear participants, after 8 minutes, we will start at 11:30. So, just wait for another 8 minutes.
Yeah.
So,
Yeah.
we'll
Yeah.
resume,
Yeah.
we'll resume after that. Thank you, sir.
Okay.
Thank you so
Yeah.
much.